Okay. Can you see my screen, guys?
Yeah.
Okay. Let's
Yeah.
get started with the hologram. Once you install hologram, it will come like you can find it here, or I guess you can find it here in that tools, in that bar, and you can bring it next to your layer and something like that. Okay. So once you install the hologram, you can go. Let me open the code. Let's say code number 2. Okay. Let me run the bifocal and start training and stop it for a while to get the meshes. Okay. Could you please close the door? Yes, thank you. Okay. Once we get our meshes there, we can go to the hologram and get the sync object. Okay. So what does it do? It syncs this object into your phone and project it in augmented reality. And in order to connect your phone into Grasshopper, you open the hologram, and once you open it, you can see like it's just looking for a QR code. Okay, so once you click on connect to device, it will show you the QR code to connect your phone. And once you connect your phone, you can see this is my phone. And now the phone is looking for a plane using a plane detection. It's in augmented reality. So once you click on the surface that you want to project your model, you can connect the sync object, and it does connect like directly and in live sync.
Sam, can we find this Grasshopper script on your GitHub?
Which one?
The one which you're using on the screen?
You mean the code 2?
Yeah.
Do you want me to update it with the hologram component? Because it's already there.
Okay.
Okay, all the codes that we've used in the previous session, it's on my GitHub repository, the DigitalFUTURES Workshop. Okay, so if you want me to update this with the sync object, I'm gonna do it, but it's just one component.
Yeah, no, we can do that. I just wanted to confirm it's on GitHub.
Yeah, all the sessions that we've recorded, it's gonna be on YouTube, and all the assets and the presentation, it's available in GitHub. Okay. So let's get started with our new session. Okay. Today we're gonna talk about the supervised learning, and it's the opposite of supervised learning. Unsupervised learning, you provide the data set and the machine train the model to try to find the relation between this data set, and we use different methodologies like Cohen network. So you see the grid or the network tries to correlate between these inputs. But in supervised learning, we go with the labeled data, which means we provide the input of the data, of the raw data, and the outputs as annotation or as labels. Let's take that for example. So supervised learning refers to a category of methods in which we teach or train the machine, while guiding the algorithm model with labels associated with the data. So in supervised learning, we provide the input data, and the output data that we provide is going to be the annotations or the labels. So the model trained based on this input and the output and give you a prediction. The unsupervised learning give you a clustering. You know, in the previous session, we see that the Kohanen tries to predict all the relation between these inputs as a grid or as a network. So we call that clustering, but in supervised learning, the output is gonna be either prediction or classification. So supervised learning can give the model the ability to predict what's the input. So once we input that apple or fruit, it's gonna know it's an apple based on the input data and the output data, which is the annotations. So in the previous session, we talked about the method or algorithm to use unsupervised learning, which is the Kohanen network or SERF organizing maps. And the supervised learning has different models or different algorithm to train your supervised learning. So if we're gonna talk about the backpropagation algorithm, resilient backpropagation algorithm, and evolutionary algorithm. Do you know, guys, or have you heard about the evolutionary solving before?
Yeah, like
Uh,
Wallacey, Octopus.
yes, thank you. And we see the default or the embedded component with the grasshopper is Galapagos. So it uses the evolutionary solving. Does anyone know what does the evolutionary solving to your code?
It's primarily used for optimization, right? Where you have multiple criteria for which you want to find a solution, and then you run generations of, similar to what we did last time. Like you run multiple iterations, and the engine tries to find a solution which complies to all the criteria that you set.
Yes, exactly. Thank you. So it takes all the possibility as a number of population, then the number that gets like really near or find the criteria that nears that fitness point, it gets evolved to the next generation or the next iteration. So it's based on selective the best parameters that would lead to the fitness point or the perfection in our cases. So we can use it as a supervised learning because we provide the output and we provide the input. If you notice in our previous session in unsupervised learning, we provide only the data, right? There's no output. That's why this is called unsupervised learning. So it tries to predict and find the relation between this raw input data. But in the supervised learning, it's learning under supervision. So you provide the label data to know if it learns correctly or not. So there's some matters of the back. We're gonna use in this session. We're gonna use the resilient back propagation algorithm. But before I'm gonna show you the type of, I'm gonna talk about the type of neural network. We hear about artificial neural network. There are like around 7 to 8 types that I've used personally. And today we're gonna talk about the feed forward, which is the most common type of neural network. We call the feed forwarding neural network. So I brought my whiteboard. I hope it's clear to you guys. So I'm gonna talk about it. Sorry. Can you guys see the whiteboard? Let me check.
Yes, yes.
Is it clear to you?
For me, it's
Yes.
clear.
Okay.
Yeah, for me too.
So what does the feed forwarding neural network? Feed forwarding is
Sorry,
self-explanatory.
Sam, I can't see the topmost part. Can you adjust it? Like, yeah, now it's okay.
Everything's okay, guys? Yeah, so we're talking about the feed forwarding neural network. It's pretty straightforward. So we're talking about the behavior of that neural network. So we have the first layer here, we call it the input layer, and we have the middle layer, we call it the hidden layer. The more hidden layers we have, we call that not machine learning, we call it another term you've heard about it, it's called deep learning. Deep learning, which means we have multiple hidden layers. But in that case, or in this session, we're not gonna dive deeply in deep learning. We're gonna talk about machine learning, which means at least one hidden layer. And the last layer, we call it the output layer. So feed forward neural network, which means the input goes to the hidden layer and the hidden layer goes to the output layer. And there's another type of neural network which we call it the current neural network, which means the current neural network, when we have an input layer, then it goes to the hidden layer, just like this, okay? And the hidden and the output layer becomes the new input of the input layer. The output layer becomes the new input of the first layer. This we call it the current neural network. So when we talk about feed forwarding neural network, it's pretty straightforward. It's from the input to the output. And the current neural network, the input to the output, then the input. So it goes as a loop. Is it that clear to you guys?
What happens in the hidden layer?
What?
What happens in the hidden layer?
Yes. We're gonna talk about it in deep now in the session. So, but what I wanted to share is the definition of the feed forwarding neural network. The back propagation, it starts to learning backward, which means it takes the output and learn why we take or why we have that output in the hidden neural network. You know, the back propagation, it comes like, I'm gonna learn this model by I'm gonna train this model by knowing the output layer, then learn why did we reach that input layer using the hidden neural network. So the behavior of the neural network, it goes from the input to the output, but the back propagation algorithm, it takes the output and learns from the previous layer. Understandable? Now we're gonna talk about the hidden layer and how does it process inside that hidden layer. I mean, it gets the input, but what happens inside the hidden layer, I'm gonna talk about it briefly now. So we're gonna talk about the activation function once we know what happens inside the hidden layer. So this is the hidden layer. It contains node, what we call it neurons. What happens inside the hidden layer? We get that input from each input from the input layer with the weights, which means the priority or the importance of that input. We generate that most of the time randomly. Okay, then inside the node, it gets to sum or to add all these inputs all together to give me the output. Okay, and the activation function, it measures what happened inside the node, whether to define it as an activate node or not. So if we're going to talk about the activation function, it defines the output of the neural given a set of the input, which means the activation function decide whether to activate that neural or that node or deactivate it, which means the output of the activation function, it takes all these parameters, the inputs and the weights, which mean the weights, as like I said, it's the importance of that input, and it calculates everything inside and give it to the output. But the activation function decides whether this output it's in higher positive value or less value. The more value it gets, you get that neural activated, and the less value that it gets this neural deactivated. So that's what happens inside the activation function. So we need, as an input from the input layer, we need the weight of that input, how much it, if it's important to you as an input or not. The priority of these inputs becomes like a part of the weight. So more weight, more important; less weight, less important, and that will be decided inside the node. And the activation function checks if that the result of this combination as to be activated inside the node or not, to be taken to the output or not. Okay, I'm gonna like describe it in depth within an example. Okay, so let's get started with the here. And the example we're gonna take, we're gonna write a code that can predict the name of a space. So we're gonna provide, we're gonna give that model multiple spaces at a data set and give it a label and let it learn from this data set and predict the name of the test space. Okay, so if you go to Rhino again, and let me start. Okay. So I've established these spaces here. So we have in different areas and different width and length. Okay, so we have these spaces at a data set. The first one we have it is, let's say, a bathroom, and the second one is a studio, and the third one, the second one, sorry, it's a room, and the third one is a studio. The fourth one is a medium apartment, and the fifth one is a big apartment, based on the length and the width and the area of these regions. Okay, started. So first of all, we're gonna take this and insert them inside Grasshopper. So we have to take them inside in order. Okay, so the first data set and the second data set and the third data set, the fourth and the fifth list. So let's start in order. Okay, let's call it spaces. Okay, each one of this category has I guess, no, it's 6 items, yes. So the first item, we call it bathroom, and the second one, we call it a room, and third one, we call it studio. Fourth one is medium apartment. Okay, and the last one, we call it big apartment. These are the labels of this data set. Okay, so now we have the spaces and we have the labels, and each one has to have like the same label. So that's why we took them inside in order. Okay, so we have to generate for every label like 6 items of every label, and in order to do that we're gonna use duplicate, a component called duplicate data, in order to duplicate these labels based on the number of the list on each list. So we have number 6 based on our data, and we're gonna graph, because I'm gonna generate like 6 items from each category. So I'm gonna graph that input and flatten the output in order to get like 6 duplications of every item here, because without the graph it's gonna generate that, it's gonna go on that list over and over, so like that. So in order to have every to have 6 duplication for each item, we're gonna graft the data here. Okay, these are the labels. And these are the spaces. Now I'm gonna extract the features manually from these spaces to give it as an input data to the model. So I'm gonna take the area of each space. Also, I'm gonna take the length and the width of each space, because we're gonna provide it as an input data, and the output data is gonna give me the labels of each space. So in order to get the area of these regions, we're gonna have the area component. It's going to give me the areas of these regions or spaces. So we're starting with the bathrooms, then we go to rooms, then we have studios, then medium apartment, then a big apartment, in order. So now we have the area. We're gonna get the length and the width of that region. And in order to do that, we can get it in two ways. The first way, we can get it from the surface, and these surfaces we can get it from the dimension component. So it's gonna give me the length and the width of each space. Or we can get a bounding box for these surfaces, and then get the deconstruct box. It's going to give me the x and the y's as a domain. Okay, and I'm gonna deconstruct the domain to get the end and the start and subtract them from each other, just like that, with a subtraction. The end minus the start. It's going to give me the same result as the UV dimension. So if you use that way, it's totally fine. If you use the UV dimension, it's also fine. Okay. Now this is the first input for me, the areas. Okay. And this is the second input, which the length. And we have the third input here, which is gonna be the width. These are the main parameters for my model. So now I need to remap them from 0 to 1 in order to get them inside the neural network. Why do I need to remap them from 0 to 1? Because once they are in the range of 0 and 1, it's easy for the model to be trained, you know. Having like a high results or high numbers, it's probably fine, but if you want to look for more accurate results, have them remapped from 0 to 1. And in order to remap them we need to have a remap numbers component. We take the value of these areas, and the source is gonna be the minimum and the maximum number. It's gonna be a domain, which is the minimum and the maximum number of these areas. And we can get it from the pound component. Pounds gonna give us the minimum, the domain, which is the minimum and the maximum of this area. So now we have from 6.4 to 305. So these are the source, and the target by default is gonna be from 0 to 1. So now we have these areas from 0 to 1. Okay. Now we need to remap the length and the width also. Now, since we have all the inputs remapped and ready to get fed into the neural network, we can gather them using Entwine. Like in our previous session, we use Entwine to collect this data, and it will give us 3 vectors, which it's not what we need. We need like a 30 vector. Each vector contains these inputs. Every vector or input vector needs to have specific input. So this is the area, and this is the length, and this is the width. So we can't have like 3 branches. We need a 30 branch, and in order to get that, we flip our tree structure. So we had like 3 branches, and flip matrix takes the number of the items, it becomes the branches, and the branches becomes the number of items. It just flip the data structure. So now we have these. Okay. Then we move into Lunchbox and get our neural network trainer. Okay. So the neural network, the inputs in supervised learning, like we said, we have the inputs as, let me show you, the input, the raw data as an input, and the annotations as the output, and it's going to predict or train within these inputs. So we give it the training inputs, and the training outputs is going to be the indices of these labels, because these are strings and the type of data here are floats or numbers. So we're gonna get the indices of these lists, and in order to get the indices, we're gonna use series component, and the count is the list length of these labels. So we have 30 labels here, and in order to get the number of items inside the list, we use list length. List length gives us the how many items we have inside the list. So we have that as a count, and the step is 1, and we start from 0. And now we have the indices of the labels. Okay. Now we provide this as input data, but don't forget the difference between these 2 structures. This is with multiple branches. They need to be matched inside the neural network. So in order to match them inside, we graph the output. So now, okay, let me graph it from here in order to show you. So if we get a param viewer here, and the param viewer there, you see the number of branches are matching. That's why we had to graph the indices. Now, the number of hidden neurons, the more hidden neurons, more accuracy, yes. Okay? But In this example, we don't need like more than 7 to 8 hidden neural networks. So we can say 7 for the hidden neurons, the middle layer. And the learning algorithm, we're gonna use the resilient backpropagation. I've explained the backpropagation, but the resilient backpropagation is faster than backpropagation. Also, it could take the activation function more than a 1, which means the backpropagation accepts a function or the result or the output of the activation function between 0 and 1. And since we are providing the training outputs as indices, which they are more than 1, bigger than 1, so we move into the resilient backpropagation. And the activation function here, we use the identity. We're trying to identify this list of data. Okay. The alpha simply is the learning rate. Okay. It's the same as the learning rate. So when we say 0.95, it's just alpha is the learning rate, exactly. So the iteration, the number of repeating or the epochs, let's say 1200. So this is the error that comes from the let's say the activation functions and the gradient of these weights, because we generate random weights, random priority of these inputs. It keeps trying to find the proper weight for every input. That's why the output of this node becomes a number, and it gets subtracted from the output and finding the margin error. And the learning rate is the acceptance of that error. Okay, so you see, the more iteration would get us less errors. Okay, and the less dynamic here, we can see it from the start. See the starting. So once we reach a higher, start to get lower and lower. So let's get back to 95. So the error is around 2%. Okay, now we have the trained neural network. The trained neural network. We're gonna go and get the neural network tester. It takes the trained neural network and we give it that a test input data in order to predict the outputs. We don't see that in unsupervised learning. We see that only in supervised learning, because the idea of unsupervised learning, like I said before, it's clustering, where the supervised learning, it's about classification and prediction. So let's try to find here. I made a layer, I called it Sam, so I'm gonna call it again using geometry pipeline. we have geometry pipeline and the name of the layer Sam, and the type of geometry that I wanted from that layer is curve. So it automatically selected that curve. But before doing that, I'm gonna tag these data set using with the labels using the 3D tag. So the locations are the centroid, and the text are these. Justification is gonna be in the middle center. But the size is going to be 0.5. I'm gonna hide these. So we have the bathrooms, and we have the rooms, and we have the studios, medium apartments, and big apartments. So now we have that test data. We need to extract the feature like we did in the data set. So we're gonna go with, we're just repeating the process that we did here. We extracted the area and the length and the width. Okay, so we have this surface, and we can get the area with the area component. So now we have the area of it. Okay, now we need the length and the width using dimensions. Okay, now we need to remap these values to 0 and 1. So the value of the area is there, and the source, the same source from here, from the original data set. So these are the area, the length, and the width. So we're gonna use the source. This is the area, so we're gonna use the source from bounds from the source, and we need to remap. Remap the second one, and we do have the U, and the source is going to be the second one because the same as a U, and the V also is going to use the bounds from the V parameter. Okay, now the mapping would give us the a value from 0 to 1. So it could give us more than 1 actually. Like here, if you see the domain, the maximum is 305 for the area. So if we scale it like higher, that will give us more than 1, which is totally fine. Okay, so now we have these values. We're gonna collect them using entwine, combine this data using entwine. Now we have this 3 branches. We can either flatten that list, or we could just use flip matrix, and we're gonna provide it as a test input. It's going to give me the number, and that number is going to be the output, which means the index from these labels. So I'm gonna deal with this output as an index for the labels from here. So I'm going to use list item. And the list is going to be these list of data. This one, labels. Now we're going to project that or tag it inside this region. So using like tag text tag 3D, the location is going to be the centroid, and the text is going to be the output. The size is going to be 0.5. Sorry. Justification is going to be in middle center. So now we have a prediction of the input data here. So once we try to find, it's going to give me the prediction of the entered region here. So medium apartment is going to room, medium apartment, studio. It's a bathroom, big apartment, and so on. So this is the first example of how to use supervised learning. Do you guys understand what supervised learning is? It tries to predict what is coming from your input and the output data.
Yeah, I mean, Sam, I have two questions.
Yeah,
First,
sure.
why did we train on the index ID? Like, I believe, getting the indices itself is, it's same as the name, it's not the number, but it's the ID. ID, even though it is using numbers, but it is sort of a string, right? So why didn't we input the list where you had bathroom, 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 and then so on and so forth? First is that, and second, how did you decide the number for hidden neurons?
Yeah. The number of the hidden neurons, we decided based on the possibilities. So, you know the possibilities, the holistic algorithm between a list to other list. So we have in the first layer, we have 3 inputs. Okay? So how many possibilities do we have? The first input with the second input, and the first input with the third input, and the second input with the third input, and the fourth is going to be the first and second and third. It's called the holistic. I don't know if you guys know the holistic listing. Do you know the holistic, or should I explain it here in Grasshopper? Okay, let
I'm
me
not
explain
aware.
it. Let's say we have the first. Okay, I might just deactivate. Okay. Oh, sorry. Okay, let's say we have that. This is the first curve we have here, and the second curve we have here. Okay. Now let's say this is the first curve, and this is the second curve, and we're going to divide each curve into multiple points. Now we're gonna use divide curve. Let's say 4 any number, doesn't matter. And let's say we have the second one also divided into 4. Now generally, if we make a line between these and these, it's going to line with each other. But we're gonna discuss here not the possibilities of this first point with the other points, and the second point with the other points, and so on and so forth. So we go to the something call it cross reference. So this is our list A, and this is our list B. So when we try to make a line between these two lists, we get something like that. It's the number of possibilities for each one to connect with the other list. We call this holistic. Okay? So it's the number of possibilities. Now we have the first layer. It has, let's say, it has a three input, right? Three nodes: the area, and the length, and the width. And the number of hidden neurals, it can be up to 4, because if we're gonna cover all the possibilities, we have 25 possibility for 4 and 4. So when we go down to, let's say, 3, 1, 2, 3, and 1, 2, 3, how many possibilities we have? Like 9. That's why more than 4, it's fair enough for you, okay, to have a hidden neural network, because we're gonna connect all the possibilities between all the inputs all together. So more hidden neurals, okay, more accuracy, yes, but you don't need unnecessary hidden neurals. So if you go to the 6, 5, see, it doesn't change that much, because we have like the minimum is 4 hidden neurals.
Yeah, clear. That is clear now. Thank you. Just that first question: why did we put indices as a training output and not the name itself?
Yeah, to let's say, why did we put here as the indices, not the names?
Yes, yes,
Yes,
exactly.
because when we talk about the neurals, it process only numbers, okay? It doesn't process, we're talking about functions, we're talking about calculation. So how would we calculate a string, a text? We need a number that
Yeah.
referred to that text, okay?
Right, but I mean, so in a way, when I say ID of anything, ID is also a text string, right? Like, because it's the ID, and I can't add two IDs, because I mean that is how I understand it. Like IDs, even though it is numerical, but it is still a string, because I can't add two IDs together. So that is where the question is. I mean, I'm not sure if I'm making myself clear. No,
Uh, okay. You mean the activation function as an identity, or you mean why
no,
did
no.
I choose
I,
the ID as an ID? You know, what I mean by the ID, the indices, not the ID of itself. You know, because every um, data we have here, every data that we have provided, it has like a different, features, a unique features that we give it like a unique index, not the same index. We're not talking about like zeros and ones and twos and threes and fours and so on. Every index, every item here in the data set has a unique, parameters or features, we call it here. That's why we give it like an index. So what happens inside these hidden neurals, it takes all the inputs and try to find the relation between these inputs and the outputs over and over. So let's say, why did we choose this as a pattern? Is it because of the proportion? Is it because of the area? That's why the weights are there, to
yeah,
define the priority of this input, okay? And the activation function decides whether this, yes, we can activate this hidden neurals, or we cannot activate it because it gives like a negative uh,
yeah.
result, okay, to take it to the last
So
layer as output.
maybe instead of the IDs, could we also have given area as our training output, and the training input could be just the length and the breadth?
Absolutely, yeah, yeah, sure.
Yeah, yeah,
Okay, so I'm
yeah.
gonna give you. I'm not gonna say homework. Okay, so in the next example, sorry, we let's try to define the main entrance. Okay, we give it multiple, like try it with yourself or try it by yourself. Try to give it like a data set of rooms, and the output is where the proper entrance of that room. Am I making myself clear? So you don't have an ID or an index, you have a position, a location for the output. So it might give you a result. Try to like experiment a little bit further. Uh, does anyone have a question about the space protection? Oh, and how does it work? Oh yeah, I'm sorry. So more data means more accuracy, but we have like a little data set, let's say just, I guess, a 30. So if you want like more, you can increase the the iterations, and you can increase the number of the hidden norms. Okay. Does anyone have a question? No? Okay. Now, let's say we need to save that models. Like we get satisfied, but with our trained model, we want to save it. You can just right click on that component, neural network trainer, and save your neural network somewhere you like. Okay, let's save it on the on my desktop here. Oh, I'm gonna provide it. I'm sorry. Let's say test. Okay, it's now saved on my desktop. So we have here, like, let's say we don't have that trained neural network. We don't need to do that process over and over to get our trained model. So we can go to the launch box and machine learning. We go to load model. It's going to take the file path, which can be provided from the file path container. Right click, select one existing file, and go to the disk and find our model. Let me find it here. It's supposed to be test. This is our model. Once we open it here, and it recognizes the model, and we can provide it and get our results. Okay, or sell it on Food for Rhino. So this is for our first example. Is it clear to you guys? Does anyone have any question? No? Okay. Now let's move forward to the next example. Write a code that can predict similar plan from a layout. Now, in order to reach that type of result, let's say a new, and I'm going to use bifocal. Okay, and in order to reach these type of prediction, let's say this is my outlines. I could provide it as a curve, and this is my entrance. So in order to reach that result fast and smooth, you need to provide like 100,000 of plans in order to train your model to get that, like, you know, accuracy in prediction. So you need to train more and more, get more and more data set. So for this session, I'm gonna upload to my GitHub around 80,000. It's just for you guys, for the one who's in this workshop. I'm gonna provide you a data set with 80,000 plans to try, experiment around, play around with this, and try to make your own plan prediction or plan predictor. Sorry. So let's jump into the next example. This is my plugin I'm working on. Perhaps you saw me uploading a lot of video about Spider Engine. It's about the BIM engine and the BIM tool and the PyTorch. It's gonna be available very soon. So let's move on to the next example. So these are a bunch of plans, okay, with a variety of areas and entrances and number of zones and spaces. But in this example, we're not gonna take a lot of raw input data. We're gonna use the simple input data as the area and the length and the width, and also we're gonna provide the entrance as a raw input. So let's say now, in order to move these plans inside a Grasshopper with the smoothest way, I'm gonna teach you a method to do that easily. So first of all, these are geometries, okay? And once you get all these geometries, let's say this one, sorry, okay, like these geometries are a bunch of polylines, curves, etc. So we're gonna group them all together as a one group of these objects, okay? Then I'm gonna record this data inside Grasshopper. So in order to do that, yes, you can input them as a plug as well, but I prefer this because if you wanna like analyze this plan and try to replace the doors with the actual 3D doors and actual furniture, it's the only way to provide them as a curves, as a input curves, or as a group. So you can ungroup them afterwards and try to construct the 3D perspective out of them. So now we have this plan as a group. I'm gonna record all these plans inside Grasshopper in order to get them. So I'm gonna use a data recorder, okay? And now we have sorry. And now we have data. So let's say, so once we start recording, we see this is our first plan, and then we move them just like that. See? Okay, I'm not gonna do all of them in this session. I'm gonna, now you get the idea of inserting all these plans inside Grasshopper. So now it's still recording all these plans. So I'm gonna open the code. Session 4. And get this here. Okay.
Sam, I have a question.
Yeah, shoot.
So if we have like 1,000 stopband, should we have to do it one by one?
Yeah, unfortunately, we have to do it one by one. Yeah,
Oh my God.
unless I'm gonna provide you guys, because this is a mediocre workshop, so we're not jumping deeply into C#, but in the assets, you're gonna have like a C# that is going to take all this data set and insert them as a group. Okay, it's going to be available in the GitHub repository. But I'm doing that step by step in order to understand what is happening here. So now we have all these data sets. So as groups, see, and remember to take them in order, just like that. Okay. Then we can ungroup them, and once we ungroup these blocks, it's going to define them as a branches. Each branch has different number of curves, depends on the size. So in order to get the area for this plan, how do we do it? Simply by bounding box, and right click on that bounding box and get the union box. So now we reach the level of the previous example. We have them as a rectangular. Okay, so now the bounding box can go to, technically it's a flat box, so it's a surface, and the flat box and the surfaces, we can get the length and the width from these surfaces. Also, we can get the area by using the area component. yeah, the area. And we're going to flatten this. If you don't flatten, it doesn't matter. Yeah, we're not gonna try to flatten the outputs because we're going to flip, entwine them and flip the data structure. So this works. So I'm gonna remap these values as let's say the values, and the source is going to be the bounds, of course, for all these areas, and the target is going to be from 0 and 1. Same for the U, for the length and the width. So bounds, source. So we now have these. We can merge them because we don't need to entwine, combine them, and then flip. They are already graphed. So technically it would give us the same data set that we wanted. But in addition, we need to define the entrances of each plan we have here, and to define that we're going to use a point and try to multiple points and get the orders, coordinates, and get the location of these entrances. Just like that. So I'm not going to do all these. I'm gonna get it from the from here, the entrances. So Control C and Control V. Now we have these as entrances. Now after getting these, the location of the entrance of each plan, we're gonna provide it as a 0 and 1 to the emerging data. So we need it with the relation or related to the surface itself. So in order to do that, we're gonna first of all project it on the closest curve of the surface, which is the outlines. And to get that point to the closest distance possible to the curve or the main curve of that plan, we're gonna use the CRVCP, the curve closest point. We need to project it to the nearest part of the curve. So we have these points, and the data from the surfaces are grafted. So we're going to graph these points and connect it to the surface. Now, you see this is the surface, and we need it like next, the nearest possible to the boundary of this plan. Now we hide this. We have this point. We can simply get the evaluation of that point, or get it the UV coordination of that point on that surface. So in order to get the coordination UV of that point in this surface, we're going to use surface closest point. It would take the point and the surface, and we're going to reparameterize the surface from 0 to 1. Reparameterize. What does reparameterize do? It just remap the U and the V from the original domain or range to 0 and 1. So we have from 0 to 1 and from 0 to 1. So we're gonna reparameterize the surface we have here, and that would give us the UV point of this specific location from 0 to 1. We can check that from the panel. So now we have 0, 0, 0, 1, and so on. So now we can get this UV point by deconstruct point in order to get the U and the V, and provide it to the merge. So now we have extra data from the new entrance. So x1, now we have 5 data. Then we're going to provide the indices of this data set apartments. So in order to do that, we're gonna get the list length, and we're gonna make a series to get all the indices of each plan. So the count is the length of that list, and it's going to give us the all the indices of this plans. Okay, so now we have the indices, and now we have the raw data. It won't, to be honest, it would not predict properly, because as a architectural perspective, it's hard to make a plan just from the length and the width and the entrance. There has to be more and more values or parameters, like the windows, the number of the rooms, the circulation, the cross circulation, the ventilation, and so on and so forth. But we're trying here with the simplest example to do that. So we have this raw input data. We can go to the machine learning trainer and get the training input, and get the training outputs as the indices. Now we have 5. We have 5 inputs, so we need, like, higher than 9 hidden neurals in order to get more accurate models. If you put it as a 8, 7, it would get less. You would get less accuracy, but the more hidden neurons, the more accuracy, and the unnecessary hidden neurons will get processed, but it's just wasting of heavy operational method. So let's say we go for a 9, and the learning algorithm, it's just resilient back propagation, and the activation function is identity. You know the difference between the resilient back propagation, you can read more about it, and the back propagation just provide the the learning rate and the momentum of each learning rate, which the learning rate of each neuron. But the problem with backpropagation, it must get the output from the neuron as a 0 and 1. And since we have indices, so we have like more than just bigger than 1 or larger than 1. So we can't use backpropagation. We can use the resilient backpropagation. Okay, here, and the activation function, it's just the identity. The identity, it's just passing, getting the result from the processing or the sum inside the neural, and it passes through the output. So it doesn't do anything, to be honest. But it helps you to get the a value more than just 1, or sorry, larger than 1. So we have the activation as identity, and the alpha is going to be 0.95. And the iteration is going to be 1500. So more iterations, more processing. Okay, so now we have all these things processed. We can use the this one as a okay, let's take this as a curve and get the entrance. So that curve and that, the entrance, we're gonna extract the feature from the curve and the entrance by using area and the dimension, and getting the points to these are the curves and the point. This is gonna be this is okay. Putting up these values all together, the value of the area, the U, and the V. And the points, we're going to get, don't forget the sources as well. Okay, the points, we're going to use surface closest point. The surface is reparameterized as always. The point is just a point to get the U of V. We can now deconstruct the point to get the location of. Okay. Now we have all this data. We can merge them. All together. And now we can bring our neural network tester, which can be in the launch box. This is our trained model, and this is the input data, which would give us a number or a float number, which is a predicted index of these lists. So if we do that, a list item, and take that index from that, let's say no, from that list. Yeah. So this is the predicted based on the area and the U and the V dimension. And once you change it, try to change the entrance, it goes, see, where the entrance is up high, trying with the similar areas. So the length and the width are good parameters, but not an accurate parameters for a plan prediction. You could try by yourself and add the number of the spaces, the location of these spaces as a raw input data, the location of these spaces and the location of these windows here. So you could get more and more accurate. Also, the number of the plans here is very, very, very low. So we have around 30, I guess, or 41 plan. And the data set that I'm going to provide, I'm going to send it individually to your email, because I'm not going to share it on GitHub. It has around 80 to 82,000 plan, and I've used it personally in that in my my model to get that. So you can use it like here, predict it. So I'm gonna provide it to you like individually. So now we have the index here. We could bring the plan to see it, but it's gonna be stupid. But yeah, let me bring it. You're very welcome, guys. Thank you so much, and thank you for supporting Digital Futures. This organization is trying to share the knowledge across the world for free, of course. So we try to bring the plan over here. We can use just orient so the source is going to be the index of the area, but it's gonna be flattened. So it's going to give me sorry, the centroid, sorry, not the centroid, yes, it's going to give me the centroid here, the source, and the target is going to be the centroid here. So source, the yes, and the geometry is going to be this one. See? So changing, look, yeah, the model is trying its best, but it's not, accurate. Okay. So, is everything like clear to you guys? Does anyone have any question?
Sam, just an observation.
Yeah.
And it leads to my previous question, like question from the previous code that previous example that we discussed.
And this
I
session
think
or the older one? Yeah. In this session?
Yeah, the previous one where we were doing with the name tags.
Yeah.
Like,
Okay.
yeah. So I feel that IDs as a target output works because you have input the data in sequence. Like you have all the boundaries for bathrooms together. In this case, the small apartments were selected in sequence, and then the larger ones, and so on and so forth. But suppose the data set is random, where or you can have big apartment, big, then small, medium, and if it's totally random, then in that case, giving ID as a training output will give inaccurate results, right? Like, am I understanding it correct?
Yeah. Let's say we have a random data set. Random data set, which means it's not fit to be in supervised learning at all. What do we do if we have a random data set? In our previous session, we learned how to cluster these data all together. To cluster all this data and to repeat and to find the correlation between this data. So we use unsupervised learning to cluster the data, and we use another model to train our neural network. So it goes in two phases. The first phase to cluster, and the second phase is to classify and predict. That's why that's the only way to do, because when you talk about supervised learning, it's like we're talking about supervision. You supervise the learning by yourself, so you cannot learn as a human being from random. Let me like teach you something, then goes to another something. It's not a good behavior. Now, if you want me to try, let's say, if you want me to try to shuffle, jitter, right? Let me shuffle these data, okay, all together and see what happens here, okay? Does anyone have any other question while I shuffle the data? Okay. So let me try to, jitter this list. Before doing that, let me try values and list here. See? Do you see what happened? So
exactly. So it's not working because the indices here have no meaning to
thank you.
This data.
Yes.
Either it should be area or length or something which is irrespective of the ID. That's why I was saying in the previous example that ID in a way is a string, right? And it has no meaning when we are training the model and getting the output.
Yeah, exactly. Thank you. So I'm using here the ID because my data is already annotated and in order, okay? Because it's going to an item to another one to another one. So it's going from the mini the mini studio or apartment to the biggest one. So I'm trying to teach the machine to learn about the little apartment or the smallest plan to the biggest plan. That's why I'm using the ID here. So it does know how the correlation or the relation between the smallest to the biggest. But when I jitter the data, so it can go from here to there, and it doesn't
Exactly.
understand what's happening to the data. So then the hidden neural network doesn't know, and I'm using the identity. So the identity as activation function, it just passes all the result without it checking the network. Okay, so
Correct. Yeah.
that's why we provide like a high area, but it gives me like a little studio, so it doesn't work. That's why I'm using the ID here. But if you have like more raw data and more output as a raw data, for example, you can try it and see what comes as an output. You can provide the location of these spaces. As you know here, there's a spaces, zones, we call it zones. Okay, we can provide the location of these zones, the area, and the length and the width, and the output is the prediction of the entrance. Reverse what we're doing here. So you provide as a raw input data the zones location, let's say a centroid of the center of every zone, and we provide the uh, length, sorry, and the width and the area, and the output here we're going to provide the predicted entrance. Okay, and see what comes up. Let me see, let me check. Uh, yes, about selecting the data, there is a way using like coding, like a C sharp, okay, or Python. You can make it like with the easiest way to select the data. But since this course isn't about coding or learning C sharp, so I'm gonna provide you this component like in the, you're gonna find it in the repository, okay? And yes, exactly. Yes. That's why in supervised learning, we try as much as possible to provide an ordered, annotated, labeled data as much as possible in order to get a good trained model. Because, like you said, like you see, for it didn't give me a good prediction. And if we go to the error, I guess we see like the error in the first prediction is in the first iteration, it's 1.3, which is like very high. It's supposed to be from 1 to 0. So that's why we use different data. Does anyone have any question before ending this session? No? Yes? Okay.
Sam,
Yeah.
can you recommend any resource from where we can get such data sets and practice, like apart from the one which you will provide?
I'm sorry, could you please repeat that?
I'm asking, do you know any resource or website from where we can, get such data sets to practice?
Yes, I'm going to provide you multiple like repositories in GitHub and multiple
Yeah.
websites you can get the data that you want. Like I'm going to provide you like let's say websites that use like share this data for free. You can download it, but you need some clearing, matching. That you need some data cleansing, okay, for this data in order to use it directly. So let me also provide some books to learn more about these functions. Like this workshop, it's uh, like really let's say in short time, and we have like 3 or 4 sessions to do it. So I cannot explain everything. I cannot explain everything in the machine learning or in deep learning. So I'm trying my best to go through it and use it in like design and computational designing. But hopefully, like next month, I'm gonna also make a workshop, like let's say a 30 session, just from A to Z, from zero to hero, in just artificial intelligence, purely AI and purely machine learning and deep learning, inside Grasshopper and outside Grasshopper as well. And it's not, most likely it's going to be for free as well. So please read more about the learning algorithm, backpropagation. Read about it. Read about the evolutionary. Read about Levenberg. Read about all this learning algorithm. Read about the activation function. Why did you use identity? If we use any other activation function, it will give us just the first one. Whatever you change, it's gonna give me the first one. Do you know why? Because the activation function, the other activation functions, the range or the result of this activation function is between 0 and 1. So you cannot provide a training output as an ID. The only way to provide it as an ID is to use identity activation function to pass through it, even if it's higher than 1.
Sam, you know,
Yeah.
do you mean that it will consider only 0? Because it's only between 0 and 1, then it considers 0 to 0.99, and then it will only consider the first one, which is 0.
I'm sorry, could
That's
you
the
please
reason.
repeat your question again?
When you mentioned that it's only between 0 and 1,
Yeah,
right?
the result, you know, when we talk that, like, f, the function of x,
As a Boolean.
1 division, let's say the sigmoid equations, 1
Yes,
divided by
as a
1
Boolean.
plus, yes. So the result of this equation, it's like sine and cosine. It's between 0 and 1. So the result or the output of this activation functions between 0 and 1. So the output here is going to give me, you know, a 0 and 1. If we try any other activation function, it's going to give me a 0 and 1 and 0 and 1, which is not gonna work.
Just a true or false.
Yes. So the 1, which means this neural is activated, and the 0, which means this neural is deactivated, like I said before. Okay?
Thanks. Yes.
That's why we use the identity. Identity is, like I call it, the dummy function, which is the f of x equal x. The function of x equal x, which is x equal y somehow. So it just passes the result to the output. That's why I'm getting higher than 1. Okay?
Thank you.
You're very welcome. Does anyone have any question? Okay, let's continue to... now we have learned the unsupervised learning in the previous session. Now we know the supervised learning. How do we embed it in architecture besides plan prediction? Do you guys have any idea? Does anyone have any idea, even in the comments? Okay, think about it, brainstorm. This is the way of thinking. This is evolving your mindset. Okay, thank you. Ahmed says architecture style prediction. Like, yes, you can use supervised learning by providing the inputs of multiple styles in architecture, and you find the features in that style, and then provide as a test input any style of architecture and get you what style is it. So think about evolving your mindset. Learning about skill sets is pretty easy. Like we learned today about supervised learning, a bunch of videos, thousands of videos about machine learning, but these are just a skill set, learning something new, but evolving and brainstorming to find an idea, to invent an idea and use it inside architecture or design or computational design. This is the value that we're hoping to get. Thank you so much for attending the second session. The third session is going to be, let's talk about a little bit of GAN, Generative Adversarial Network, and dive a little bit in the deep learning. I'm sorry. I don't know, guys, if you're ready for the deep learning or not. I'm a little bit worried, but let's say, guys, you're ready for the deep learning, okay? So we're gonna go dive deeply in the deep learning. Deep learning, which means multiple hidden neural network, more than one. And talking about the GAN, which means talking about the convolutional neural network, which is the extracting features from the images and synthesis data. So we can use this also, this technique, to generate different plans, okay? And if you go to my Instagram account, to the highlights, go to the architecture AI, you will find how I synthesize data using the GAN. Okay, by using Google Colab. Yes, by using Google Colab. Okay, guys, thank you so much for attending, and I hope to see you in the next session. Bye bye. Thank you.